Hey everyone, and welcome to my channel. In this video, I'm going to be covering calculus, and you might be wondering why you ran into calculus on a physics channel. Just like arithmetic or algebra, calculus is a system that allows us to work with and understand different variables. We're not going to be solving any difficult problems or anything like that. This is just going to be conceptual. We're going to talk about the ideas that particularly relate to mechanical physics and how we can better understand the relationship between movement and forces. Okay, so what is calculus? Fundamentally, it is the examination of the relationship between a rate of change and a sum or total change. So it basically answers two questions. One, if something is changing at a given rate, then how much will it change over a given amount of time? Solving that problem is called taking the integral. The other question is exactly the opposite. If something has changed by a certain amount, then we would ask how fast has it been changing? That's called taking the derivative. Just as a quick example, if we have a car moving at 60 miles an hour, the change that we're talking about is where the car is, its position, and that's changing 60 miles every hour. So the 60 miles per hour is an example of a rate of change, and then we can look at the individual distances that it would have gone at any given point in time. Those are examples of the sum change that will have occurred. Obviously very simple, and you've probably solved this type of problem before using algebra, but we're going to use it to demonstrate what an integral looks like. So just to reiterate, when we solve an integral, the rate of change is known. In this case, that's our speed, 60 miles an hour. And we are going to calculate the sum total change over a period of time, or how far this man travels. What this would look like with calculus notation is this little equation right here, and this fancy little squiggle is literally just an S. In English, this equation would read, what is the sum or total change from 0 hours to 4 hours if the rate of change is 60? The genius solution to this and any related problem is that the sum change is equal to the area between the plot line and the curve. Okay, so I've gone ahead and shaded in the area that we're trying to find. And obviously, this is really easy. We can just use it how we would find the area of any rectangle, 4 times 60. And if we solve this integral with the rules of calculus, we come up with the exact same equation, that 4 hours times 60 miles an hour is 240 miles. Okay, but what would we do if it was a more complex situation? In this case, imagine this man is driving on the highway for 2 minutes. He comes off his exit ramp and comes to a red light where he waits for 30 seconds. Then when the light turns green, he picks up speed initially linearly, and then he starts to kind of taper off as he continues to gain some speed. Right, the way we would solve this is the same. We're going to find the area between the curve. We would break this up first into 5 segments, and each of these segments can be represented with a different mathematical function. 2 of these segments, the red and the orange, have curves in them, so we can't find the area how we would with traditional methods, and the rules of calculus must be used. I've gone ahead and done that, taken the integrals, and I've color-coded. This is the distance traveled during each of these time periods, and we see that over this entire 4.5 minutes, even though his speed is changing, we're able to calculate that his total distance traveled is 2.86 miles. And this is the process that would be used for any such definite integral, regardless of the complexity of the equation. So now moving on to the derivative, which is exactly the opposite question. In this case, we know what the position is or how much change has occurred at any given point in time, and so we are going to calculate the speed or the rate of change at any point in time. In this example, we have a rock or any object being dropped from 100 meters in the air. This is a graph that shows its position over time, and this is the equation that represents that, taking into account the acceleration due to gravity and our starting position, 100 meters. Here's the notation for taking the derivative of an equation. And when we take the derivative, we started with our equation that represents height. The derivative gives us a new equation that represents velocity. So at any time we'd like, we can go ahead and plug in at 1 second. We plug that into our equation for velocity and find that the rock is moving downwards fairly quickly. We go ahead and plug in 2 to find its speed at 2 seconds. We find it's moving downward even faster. Same deal at 3 seconds, downward even faster. Just like the integral uses the area to calculate the sum change, the derivative has a secret as well, and that is that the instantaneous rate of change, meaning the speed at any point in time, is equal to the slope of our curve at that point in time. You can see, as I've highlighted here, at our 1, 2, and 3 second marks, the slope, which is the tangent to the curve, is downwards, getting steeper, steeper, and steeper, as we calculated using our derived equation. If we look at the notation for the derivative as well, you might remember calculating the slope in high school or middle school, something like that, which was rise over run. This dh represents change in height, or our rise, and this dt represents change in time, or our run. So quite literally, when we take the derivative, we're finding an equation that gives us the slope of a line at any point in time. So we started with speed, and taking the integral of speed helped us to understand the position. Going backwards and taking the derivative of position helped us to understand speed. This can be extended to acceleration, and thanks to Sir Isaac Newton, we know that acceleration is directly proportional to force. So this is probably what has the most applications in exercise sciences. It can also be extended to jerk, which likewise helps us understand changes that are occurring in force. This is much less common, but it does have some applications in kinesiology and sports medicine. But certainly position and speed are things that we think about all the time. I think that understanding how those are mathematically related, and especially how they are mathematically related to acceleration and considering the forces, helps us think about the way that we're moving and muscular forces that we're producing, or reaction forces. It can help us fine-tune our movements, exercise better mechanics, or consider risk factors, things like that. Plenty of applications. So let's go ahead and look at one specific example. So in this example here, we have a bench press. I've gone ahead and represented this with a trigonometric function. It's not going to be exactly representative of the motion you would actually see in a bench press, but it's certainly sufficient to demonstrate the applications of calculus. As you can see, the bar is lowering to the bottom of the press, and then we raise it back to the top, and we repeat. We take the derivative of this function, and we are given a graph of velocity. Just to kind of understand what's going on here, we can see at time 0, at the top of the bench press, our velocity is 0. Velocity picks up and peaks downwards as the bar is falling, and it returns to 0 as we stop the bar at the bottom. Likewise, velocity then climbs and returns to 0 at the top of the press. So we can now take the derivative of our velocity graph, which yields a graph of acceleration. And just a few things to take note of here. We see that downwards acceleration peaks at the top of the bench press. This is when our muscles are relaxing and we're allowing gravity to take over and turn the bar around quickly. Upwards acceleration peaks at the bottom of the press, which is when we're pushing the hardest to turn the bar around and get it moving back upward again. So here we have another example. This is someone performing the bench press with the same movement pattern, but their tempo is doubled. And so what that ends up doing, as you can see, the graph is compressed. All these peaks are a little bit sharper. And so what that means mathematically is our derivatives, or our slopes, are all going to be greater in magnitude. So let me show you how that impacts muscular forces. If we look at our slower graph of acceleration, the peak bar acceleration is 2.25 meters per second squared. Note that this is the net acceleration. We have the acceleration caused by gravity pulling downwards, and we have the acceleration caused by our muscles pushing upwards. If we adjust for gravity, then the upwards acceleration produced by our muscles alone would be 12 meters per second squared. We can solve that. Assuming we're bench pressing 100 kilograms, this is 1200 newtons. Now when we look at our faster example, even just by doubling the speed, we see that the net acceleration is affected much more than that in this case. Adjusting for gravity again, this puts our peak muscular acceleration at 18.8 meters per second squared and the peak muscular force at 1900 newtons, right? So just by increasing the tempo, we have greatly increased the muscular force required to produce that movement. It's been years since I've actually solved a derivative or an integral, but certainly considering how different mechanical metrics are mathematically related to each other, it's absolutely something I'm doing in the gym every single day. So I hope you can appreciate this as well. I hope you can find ways to apply this. If you did find this helpful, please like and subscribe. And as always, if you would like professional help, head over to cabodycoach.com. Thank you.